In today's talk, we're going to use the inclusion exclusion principle to compute the t-numbers, TMN, which, as you know, counts the number of distributions of m distinct balls into n distinct boxes with the condition that there's at least one ball in each box. How are we going to use inclusion exclusion here? Well, again, let's be very clear on how we set the problem up with, say, capital U here being our universe. That's the set of all distributions of m balls into n boxes, no conditions here. Just as a quick note for later, you should be able to compute the size of U very easily. What is that? How many ways are there to distribute m balls into n boxes? Well, that's just n to the m. That's one of the standard problems. Now, in order to incorporate this condition that each box has at least one ball in it, we're going to set up our sets A1, A2, A3, etc., knowing ahead of time that what we'll want to find is the size of the intersection of their complements. In other words, A1 should be some set which any distribution meeting our condition, at least one ball in each box, will fail to be in A1. So let's put some labels here. Let's say the boxes are numbered 1, 2, up to n, and then A1 will be the set of all distributions. And by distributions here, I mean those that are counted in the universe U, which leave box 1 empty. So it's clear any good distribution will certainly have to be an A1 complement, in other words, not in A1. A2, A3, etc. will be defined similarly. A2 will be the set of all distributions which leave box 2 empty. A3 is the same thing with box 3. And we're going to keep going all the way to A sub n is the same thing with box n. Then it really is what we want to find, this intersection of the complements. Any distribution that has at least one ball in each box will fail to be in A1, A2, A3, all the way through AN. And anything which fails to be in A1 through AN will have at least one ball in each box. Now, why is it so important that this is what we're trying to count? Well, by the inclusion exclusion formula, we can write this as S0 minus S1 plus S2 minus S3, and then we're going to keep going plus and minus alternating until we get to, at the end, plus or minus S sub n. It'll be a positive, a plus sign if n is even, a minus sign if n is odd. And we've already seen that S0 is just n to the m. That's the size of U, which we computed to begin with. But it's very easy to count the other ones as well. S1, we have to subtract S1. S1 is a sum of n terms, the sum of the size of A1, the size of A2, etc. All of these have the same size. How many ways can we put m balls into n boxes with one of them empty? Well, that's really like putting m balls into n minus 1 boxes, so we'll just have n minus 1 to the nth power. That's the size of each set, and we have n of them. Now, we can also think of this as n choose 1. So S1 is just n times n minus 1 to the nth power. What about S2? S2 is the sum of the sizes of the intersections of the sets 2 at a time. Well, there will be n choose 2 different intersections of the sets 2 at a time, and to be in such an intersection, we'll need a distribution of the m balls into now n minus 2 boxes, because 2 of them will be empty, and that can be done in precisely n minus 2 to the m. And it should be pretty clear how this continues. For S3, we'll be taking intersections 3 at a time, so we'll have n choose 3 of them. Each one will consist of distributions of m balls into n minus 3 boxes, so I'll have n minus 3 to the m. And we'll keep going like that, plus, minus, etc., using inclusion and exclusion. And what do the last terms look like? Well, for the s sub n minus 1, we'll have, I'll call it minus or plus, n choose n minus 1. This will just be n. And then we'll have n minus 1 to the nth power, because all the balls will have to go into a single box. This clearly is just going to be 1. And then for s sub n, we'll have the intersection of all the sets, but for a distribution to be in the intersection of all the sets, all the boxes have to be empty, and there's 0 ways to do that. You would see, according to this pattern, that would just be an n minus n to the nth. You'd have a 0 for that last term. So here's our formula for the size of a1 prime, a2 prime, etc., and we know that that will count Tmn. Here's another way of stating the result. Tmn, the number of ways to distribute m balls into n boxes, with none of them empty. This is what we wrote down the last time, n to the m minus n times n minus 1 to the m, plus n choose 2, n minus 2 to the m, etc., all the way till we get to n choose n minus 1 times 1 to the m. We can write that in compact form as a sum from k equals 0 to n. The k is going to be this lower number. Think of this as n choose 0 times n minus 0 to the m. This will be the n choose 1 times n minus 1 to the m, etc. So I'll have this alternation, minus 1 to the k, starting positive when k equals 0, n choose k times n minus k to the mth power. We'll go from 0 all the way up to n, even though the nth term, remember, is just a 0 at the end for the k equals n term. Now, I would like you to think about this. This is a formula for Tmn. It's still not a closed form formula. It's not the nicest type of formula because it does have this sum in it, or to replace the sigma notation, it has the ... in it. So it's not what we call a closed form formula. When we first defined Tmn, remember, we wrote it in a different way as a formula. We had to take a sum over all distribution numbers, m, m1, m2, through m sub n. But we summed over certain types of distributions, namely all types of distributions where m1, m2, through mn were all greater than or equal to 1. We couldn't have any zeros since we had no empty boxes. And of course, for this to be an allowable type of distribution, m1 plus m2 up to m sub n had to equal m. These lower numbers have to add up to the upper number. Now, this is in some sense a worse type of formula because it can be very difficult to know even exactly what all the different types are over which you're summing. At least in this new summation formula, we have something very definite. We know there will be exactly n plus 1 terms. Actually n, because the last one is 0 always, so we can skip it. There will be n terms. You know exactly what they look like, and it's, in general, somewhat easier to compute. And remember, if you don't like either of these formulas, we had the recursive formula, and we used that to create the t-triangle and all of that as well.